Hi everyone, in this video we will be learning about chemical nomenclature. By nomenclature we mean the name of a certain compound or a certain substance. Okay, so we know very well that if we know the name of a particular object, we eventually know what its uses are, what its benefits are, or what the potential harm it can do to our body. Okay, so an understanding of the names and the formulas of the chemicals is a very important skill among those who are working in the field of science, right? So for this part of the video, we expect you to apply IUPAC rules in naming and writing the chemical formulas of binary ionic compounds. And for simplicity, we label them as types 1 and 2, and later on you will know why, right? So just an overview. I'm pretty sure your junior high teachers already told you the meaning of IUPAC, which is the International Union of Pure and Applied Chemistry. So it is a scientific body which is the universally recognized authority on chemical nomenclature and terminology. Okay, so it establishes an ambiguous, uniform, and consistent nomenclature and terminology for specific scientific fields. So that is why, for example, when you talk of calcium chloride in the Philippines, then in some other countries, they will also know what calcium chloride is because there is that a scientific and governing body that holds the conventions for naming and formula writing. And it doesn't end there. The IUPAC is also responsible for the conventions, okay, or the methods of drawing chemical formulas or of assigning chemical formulas and charges. All right, so let's start. So we were talking about binary compounds. So when you say binary, that means two. So they are composed of two types of elements, such as H2O, okay, so hydrogen and oxygen, or KBr, that's potassium and bromine, okay, not necessarily just two atoms, say two types of elements. Now, diatomic molecules consist of two atoms of the same type, such as H2 and O2, and you can just call them by their element name. For example, this is hydrogen, and since it exists in nature as a gas, so we say hydrogen gas, and then oxygen gas. You can also have fluorine, F2, and bromine. Okay, the bromine exists as a liquid, but if you have just Br2, then we can just call it bromine. We call them by their element name, all right, for diatomic molecules. Now there are two types of binary compounds. First is the binary ionic compound, which is composed of a metal and a non-metal, and there is type 1 and type 2 under this uh, classification. There are also binary covalent or binary molecular compounds, uh, which are composed of non-metals such as H2O and CO2, and these are very familiar elements, water and carbon dioxide. So for this part of the lecture, we will focus on binary ionic compounds, okay, composed of metal and non-metal. So binary ionic compounds, they contain positively charged cations and negatively charged anions. All right, so there are two types. So type 1 comprise those compounds wherein the metal present only forms one cation. Okay, so for example, sodium. Okay, and the metals found in the alkali and in the alkaline earth metals. Okay, also silver. Okay, silver can only form Ag plus cation. Type 2 compounds, type 2 binary compounds are those wherein their metals can form two or more cations with different charges, and most of them are found in the D block. All right, so for example, iron, which can form Fe2 plus or Fe3 plus. So based on our previous discussions, okay, ele- elements in the D block are mostly multivalent, and meaning to say they can lose a certain number of valence electrons, making them form different charges, ions with different charges. So here are the rules for naming type 1 ionic compounds. Again, these are compounds wherein the metal only has one charge. Okay, so the cation is always named first and the anion is named second. A simple cation takes its name from the name of the element. And a simple anion is named by taking the first part of the element or the root and adding IDE. Okay, so for example, AlCl3. Okay, Al forms the Al plus 3 ion, but since this is our metal, we just call them by its element's name. So that's aluminum. Okay, so Al from group 3 always forms Al3 plus. And then if you have the chloride ion, Cl minus, if it bonds with a metal, then the Cl from group 7 always forms Cl minus as an ion. So the name for this compound is aluminum chloride. All right, aluminum chloride. So the first thing that you will have to remember or to look at is that is my compound made up of a metal or a non-metal? And can my metal have a variable charge, right? So here are some simple cations and anions, and these are the most common ones. So for example, you have lithium ion, sodium, potassium, cesium, so on. And these here are our group 2 elements, magnesium, calcium, okay, barium, so on. Zinc also, and then anions, hydride, fluoride. Okay, you look at the root, which is given in blue color, and it ends in IDE. So if you have sulfur, you do not say sulfuride, but sulfide. All right. So here are a few examples for type 1 compounds. So it's usually metal plus non-metal. So most common example is table salt, that's sodium chloride, made up of sodium and chlorine. And you notice how uh, INE from chlorine is changed to IDE. Okay, sodium chloride. Another one is calcium bromide. Okay, now calcium usually forms the cation Ca plus 2, right? So if you have Ca plus 2, then if you remember, if we draw, if coming up with a chemical formula, that is just Ca plus 2 and the um, bromide ion or the bromine ion called bromide, Br minus. So crisscross, disregard the sign. So you end up with Ca Br sub 2. Alright? So therefore, you can also deduce the chemical names from the chemical formula, or you can deduce the chemical formula from the chemical names. So it's an interchangeable process, right? Another example is aluminum oxide, the one we've shown in our leads, right? So aluminum Al3 plus and oxygen O2 minus. So when they bond together, that you end up with Al2O3, following the same principle as in here. So here are a few examples. I'll give you maybe a minute to think about the answer. So if you can, you just pause the video so that you can try to work out on your own notes. All right, so the first one is potassium chloride. All right, so that's potassium ion and the chloride ion. Next one is magnesium bromide. Okay, magnesium bromide. Now, if you try to look at the third example, so you have CaO. So where are the charges here? You might think that it should be reflected. So remember that ionic compounds are empirical formulas. They are at the smallest whole number ratios. So calcium, it belongs to group 2A. So there are two valence electrons and it's ready to lose those two valent electrons. Oxygen uh, has a charge of negative 2 or 2 minus. So when you crisscross, disregard the sign, you end up with Ca2O2. Okay, now remember that ionic compounds are at smallest whole number ratios. So you just cancel them out since they are the same subscripts. Okay, or find the GCF and then cancel them out. Or in math, you say reduce to lowest terms. That's why the chemical formula is CaO. Alright, so the name there, chemical name there is calcium oxide. Alright, so pause this video and try to figure out the answer on your own. What is the name of the compound SBr2? And you have the following choices. So the answer here is strontium bromide. Okay, strontium bromide. So in the next set, we will be dealing with those at the D block. Okay, remember that these are most of the transition metals are made up are multivalent, meaning to say they can form cations with more than one charge. Okay, except perhaps for zinc, for silver. So zinc has a charge of +2, as well as cadmium, and then silver has plus 1. Alright, so there are actually exceptions to the rule. Okay, so we now go to binary ionic compounds, which are type 2 with transition metals. So metals in these compounds can form more than one type of positive charge on the so in naming, the charge on the metal ion must be specified. Okay, and then Roman numerals indicate the charge of the metal cation. Okay, and then transition metal cations usually require a Roman numeral. So here are the rules of naming ionic compounds. So the cation, still the same, is always named first, then the anion. Because the cation can assume more than one charge, the charge is specified by a Roman numeral in parentheses. So for example, when you say iron oxide, okay, you must specify which iron it is. Is it iron 2 plus or iron 3 plus? So Fe2 plus or Fe3 plus. Okay, so as for this case, you have Fe2O3. So if you reverse the key here is to reverse the crisscross, disregard the sign method. So if you are given here Fe2O3, you must know that the 3 there comes from the iron cation, all right, and the 2 here comes from oxygen, O2 minus or O minus 2. So you just have to reverse the crisscross, okay, and place back the sign. All right, so here iron Fe2O3 is composed of iron 3 plus and O2 minus. Okay, so in naming, we say iron 3, and take note that there is no space. All right, so iron is a transition metal and requires a 3 to specify the charge of the cation. Let's take a few examples of those cations which have variable charges. All right, or we say multivalent elements, multivalent metals. So we have iron, Fe3 plus, Fe2 plus. So in the old or the traditional way of naming these guys here, they usually have the Latin name and then coupled with ik or us. The ik is used for those elements which have the higher charge. Okay, so if it's 3 and 2 and there are only 2 possible charges for iron, so iron 3 plus takes the ik form, so it's ferric. Okay, and then the lower charge, Fe2 plus, is ferrous. Right, so this is for copper, you have cuprous. And then let's have another one which uses the Latin name. So for example, lead. Okay, so lead was primarily used in the Roman era, or Roman times, Roman ancient civilizations, to form their pipes, the lead pipes. And it is still now, but at a minimum level. So that's why we have the word plumber, okay? Because the Latin name for lead was actually plumbus, okay? BUS. So if you have now the possible cations for lead, the one with the higher charge, Pb4 plus, takes the ic form, so it's plumbic. And then for the lower charge, you have plumbus with an O, OUS. All right? So those are just some of the elements or just some of the metals that can form cations with variable charges. Okay, so another set of examples you have iron 3 bromide. Okay, and there should be no space, by the way. Sorry, there's a space here, but can you remove that? There must be no space between the name and the Roman numeral, right? So we can the Latin name or the transition metals using the traditional names is still accepted, by the way. So ferrous, that means FeBr2, ferrous bromide. So this comes from the ferrous ion. If you remember in our list, is ferric is 3 plus, ferrous is plus 2 or 2 plus. So that's why you have the formula FeBr2. Then compared with ferric bromide, remember that ferric takes the plus 3 form. Alright? So here are a few examples. Copper and bromine paired together. So one key in naming is that you think about whether this can form a cation with a variable charge. So we know very well that copper is placed in the D block, so it's a transition metal. So really we must dissect. Okay, so we see that there is no subscript given, but what we should know is that bromine has a charge of -1, right? Br minus. So the only way for this chemical formula to happen is that if copper also has a charge or a superscript of 1, let's Cu plus 1, all right? So that when you crisscross, you end up with CuBr. So the name here is copper 1 bromide, all right? Copper 1 bromide. The same thing happens with FeS. So you must know that in bonding with ionic compounds, sulfur has a charge of -2, right? So the non-metals will usually be your clue. Where are they placed in the periodic table? So sulfur S2, and then therefore the only way for this to be reduced into FeS is if iron has a charge of +2. Therefore, the name there of FeS is iron 2 sulfide. Or we can also ask, or we can use the Latin name or the traditional name, which is, so since it's lower, the ferrous. Sulfide. Okay, ferrous sulfide. Now look at PbO2. Okay, you might be tempted to think that it's Pb2 plus, right? But it actually isn't, because if you notice here, if you say PbO2, then you are assuming the 2 to be the charge of lead. But if you reverse the crisscross, there is nothing left for oxygen. So you are saying there that oxygen has a charge of -1, when in fact oxygen, okay, so this is not right, that's X. In fact, oxygen has a charge of -2 or 2 minus, right? So therefore, in order for this formula to happen, it must have been reduced into its lowest terms. So that is Pb plus 4, right? So that when you crisscross and disregard the sign, this is Pb Pb2O4. And since it's the simplest whole number ratios, then you in math find the least common, you reduce it to lowest terms. That's Pb O2. Alright? But the component is actually this one. The main component is your Pb4 plus ion. So the name there is lead oxide. Alright? So a few seconds to sink in. You can pause the video. Okay, so another exercise. What is the name of the compound CrO3? Okay, pause the video and think about it. Alright, so first you must think that Cr, you may think that the 3 here comes from Cr, from the chromium. So 3R plus 3. And then you are saying that oxygen will have no charge, which is will have -1 charge, right? So this isn't the case. So oxygen actually has a charge of -2 or 2 minus. So what could have happened there? Okay, so as with the previous example, it must have been reduced to its lowest terms. And the only way that CrO3 could happen is when Cr was, so if you reduce it to Cr something, it could have been that Cr was bearing the charge of +6, alright? So this is your chromium 6 ion. So that when you crisscross, you have Cr2O6. So if it reduces to lowest terms, you divide this by 2, you divide this by 2, you end up with CrO3. Right? But our component or our component cation is this one. So when you choose the name, that is actually Cr or chromium 6. Okay? Chromium 6 oxide. Alright? So pause for it to sink in. Okay, another one. What's the correct name of the compound that results from the most stable ion for sulfur and the metal ion that contains 24 electrons? So this is just a mind game. Okay, you must know a lot of things already. Okay, so pause and I'll give directly the answer. So that's iron 2 sulfide. Okay, iron 2 sulfide. So let's practice. So on your notebook, you can pause the video after each item is given, and then answer, and then check whether your answer is correct or not. All right. So here, CaF2. Pause. Answer. That's calcium fluoride. Second item, K2S. Pause. Answer. Potassium sulfide. COI. Okay, your clue is cobalt. Is cobalt belonging to the D block? Can it form a cation with multiple charges? So correct answer here is cobalt 2 iodide or cobaltous iodide. SnF2. Can Sn form a cation with a variable charge? Can tin form a cation with a variable charge? So answer is tin 2 fluoride or stannous fluoride. How about this one, Sn4? Alright, that's at tin 4 fluoride or stannic fluoride. MnO. Can manganese form a cation with a variable charge? Yes, it can. So if we must specify the charge, manganese 2 oxide or manganese oxide. Copper, Cui2. So copper can form a cation with multiple charges. So that's copper 2 plus or copper 1 plus. So it's 2 plus, so we say copper 2 iodide or cupric iodide. How about this one? Is the copper that bears the smaller charge. Okay, that's copper 1 iodide or cuprous iodide. Now silver can only form one charge. Okay, can form a cation with a single charge. So we say silver chloride. No need to indicate the charge of silver because we know that it's always 1. How about this? Can strontium form a cation with a variable charge? Okay, no, it can't. So no need to specify with a Roman numeral. So we have strontium fluoride. Last one, LiBr. Can lithium form a cation with a variable charge? No, it can't. So we have lithium bromide. Alright, so that's basically for the type 1 and type 2 binary ionic compounds. Okay, so remember the rules for one for cations with single charges and cations with multiple charges. So in the next video, we will be naming binary covalent compounds. So stay tuned, you can take a break, grab a cup of coffee, and rest.